In today's video, we're going to be talking about Atwood machines. After watching this video, you should be able to calculate the net force on some objects in an Atwood machine, along with being able to calculate their acceleration. So it's just basically an extension of what we've been doing in some of the previous videos. So let's get right to it. What is an Atwood machine? Well, basically an Atwood machine is just a pulley system that will change the direction of a force. And the magnitude of the force stays the same, so that doesn't change, but basically the direction changes. So in this picture you can see this weight is going to be pulled down by the force of gravity, and then that's going to cause this block to move due to this tensional force in the string. Okay, so it's a change in direction, but the force, the magnitude of it, is the same. So I mean, if the force is 5 newtons down, then the force is going to be 5 newtons here, but instead of down, it's to the right. Okay. Some strategies for solving problems with Atwood machines basically involves selecting an axis system so that both objects accelerate along an axis in the positive direction. Okay, so in the previous picture, I would have picked that actually gravity going down would be positive because that's the direction it's going to accelerate. We know that that block is going to move down, and that will be positive. And then for the other block, the one that was sitting on top of the table, when it moved to the right, I would have said that's a positive direction. So that it just kind of makes the numbers easier. If you start using negatives and stuff, it gets a lot more tricky. So try your best to use positive numbers as much as possible. Good free body diagrams should be constructed. Okay, so make sure you're labeling all your forces, what's going on. That's key. And then you can use Newton's law basically to set up a system of equations to calculate acceleration and the force of tension, typically is what they're looking for in the rope. Okay, so let's do some example problems and you can kind of see what I'm talking about. So here we have a 20-gram mass, which is M1, 20-gram mass, which is M2, I apologize, is attached to a 250-gram air track glider, which is M1. Determine the acceleration of the system and the tension in the string. Now, if you're unfamiliar with an air track glider, basically it's kind of like an air hockey table in a way. That air is being pushed up through this tube, and it causes this block basically almost to float in a way, so it really reduces friction. So when they say that, they're basically saying that the system is friction-free. Something else I didn't mention is that this pulley is considered to be friction-free too in all of these problems. So we won't be calculating the amount of friction, say, in this pulley. Okay, but we'll never do that. All right, so anyway, the first thing I'm going to do is I'm going to start by making a free body diagram of my two blocks. So here is M1. Okay, so M1 is experiencing first the force of gravity. Okay, unless it's not on Earth, it's experiencing the force of gravity. Now, what's going to balance that force of gravity? Well, that's the air track itself. And so you can call it the normal force, I suppose, but I'm just going to call it force of air because it's kind of like the air is pushing it up. And those two forces are going to balance each other out because this block is probably not going to just spontaneously accelerate upward. So the force of gravity and the force of the air track are balancing each other out, basically making it friction-free. There is a force that is being unbalanced, and this would be the tensional force, F sub t, the force in this rope that's pulling this block to the right. And that's going to be my positive direction for this block, is to the right. Okay. What about M2? Well, M2 is going to have, as always, the force of gravity. Unless it's not on Earth, it's going to have the force of gravity. And then this rope is going to provide some tensional force, F sub t. Now, this block, M2, must be making M1 move. So I'm going to call the force of gravity positive and the tensional force negative. Okay. So now that I've kind of set up some of my diagrams, I'm getting close here to kind of starting to look at Newton's second law. But before I do that, one thing I want to talk about is that these masses are measured in grams. Anytime you see grams, change it to kilograms. Okay, we can't be using grams to make these equations work. Okay, or else we need to use different numbers for our acceleration due to gravity. So 250 grams for M1 is really 0.25 kilograms. Okay, just divided by 1,000, and 20, I'm just going to divide by 1,000 to give me 0.02 kilograms. Okay, that's kind of important. All right. So now I'm going to start setting up some equations. All right, so let me just change my pen color here to something more exciting. I'm going to first deal with let's deal with block 1. Okay, block 1. So for block 1, I'm going to say the F net on block 1, which is going to be in the x direction, okay, because that's the only thing that's not being balanced, is equal to the force of tension, which is equal to mass times acceleration. Okay, so basically the net force is equal to the force of tension, which is equal to mass times acceleration. All right, that is my first equation. All right, I do not know the tensional force. I do not know the acceleration. That's something I'm trying to figure out. So I'm trying to figure out F sub t and A. Do I know the mass? I do. It's 0.25 kilograms. So I'll write that in up here. Okay. But basically, I'm going to stop at this point. I've set up an equation, and now I'm going to stop, and I'm going to look at my second block, because we're going to have to set up multiple equations, basically, and then kind of plug things in to make it all work out. For block 2, the F net, which would be in the y direction, but either way, it's always positive. It's going to be positive. I'm sorry, the acceleration is going to be in the positive direction, so it's going to be the force of gravity minus the tensional force, right? The tensional force is going to be pulling the opposite direction, right? Which is then equal to mass times acceleration. Now, can I figure out the force of gravity on block number 2? I can. If I take 0.02, so I'll just write that over here, 0.02 kilograms times, that's a 0, by the way, 9.8, I get a force of gravity of 0.196 newtons. Okay, so I'm going to write that in right here. 0.196 newtons minus F sub t equals to the mass of block 2, which is 0.02, and then A. Okay, I'm just putting A next to it. All right, so now I have these two equations set up. Well, what's interesting is that I can then plug some things in. Like, I know that F sub t equals 0.25a, right? F sub t equals 0.25a. So where I see F sub t here, I'm going to plug in that. Okay, so I'm going to change colors here again just to kind of jazz things up. So I'm going to have 0.196 newtons minus F sub t equals the mass of block 2, which is 0.25 kilograms, times A, equal to 0.02a. Okay, so I want to get my a's all to the same side, right? And so if I just add 0.25 to each side, I get 0.196 newtons is equal to 0.27a. Okay, so I just basically did a little bit of algebra there. Now if I do a little calculator work and I take 0.196 divided by 0.27, I get an acceleration of 0.73 meters per second squared. Not real fast, but you have to imagine this little tiny block is pulling this much bigger block on this air track. Okay, so it's not a super fast acceleration, but it will accelerate. Okay, so that's one piece. That's to determine the acceleration of the system, and then the second piece is determine the tension of the system. Okay, I'm going to change colors one more time. Basically, I'm just going to go back and look at my equations, and I really like this equation right here because the tension's the same everywhere. By the way, the tension here is the same as the tension here. Okay, so that there's no difference in it. If I use this equation and I know the mass and now I know the acceleration, I can find out F sub t, right? So basically, I'm just going to rewrite this down here. F sub t equals the mass, which is 0.25 kilograms, times A, which we just calculated was 0.73 meters per second squared. And if you do that problem, you get 0.18 newtons. And not a huge force, obviously, but 0.18 newtons of force, of tensional force, would be in the string. All right, and we just solved an Atwood problem. Let's take a look at another one, maybe a little bit more challenging. It says a 100-gram mass, M2, is hanging, and it's attached to a 325-gram mass on a table. The coefficient of friction between the 325-gram mass and the table is 0.215. Determine the acceleration of the system and the tension in the string. Okay. First thing I'm going to do is I'm going to draw a free body diagram of M1 and of M2, okay, because that kind of guides me in terms of where I go with this problem. Okay, so on M1, we have first the force of gravity, right? And then you ask yourself, what's touching M1? Well, the table's touching M1, right? And that's going to produce a normal force, right? This rope, or string, or whatever you want to call it, is going to produce a tensional force, F sub t, and then the table also is going to produce another type of force, which is the force of friction. And the way I kind of know that is because it talks about the coefficient of friction. So that sadly means we're going to have to calculate the frictional force on block M1. Okay, so there's 4 forces acting on block M1, believe it or not. Now block 2 is actually a little bit easier. You have, as always, the force of gravity, and you have the tensional force, this rope that's holding on to the top of this block. Okay, so let's first calculate some of these forces on block 1, so I kind of have an idea of what's going on here. Let's first calculate the weight. Okay, so if you do basically the mass of this guy is 325 grams, which I'm going to convert to kilograms, so 0.325 kilograms times 9.8. You get a weight of 3.2 newtons. 3.2 newtons. And that's going to be balanced by the normal force. The normal force is also 3.2 newtons. Okay. Now, why do I need to do that? Because you're like, well, these two forces are balanced each other. The reason why I'm interested in that is because I want to calculate the force of friction, which, if you remember, the force of friction is basically mu times the normal force. Okay, mu times the normal force, where the mu, or the coefficient of friction, is 0.215 times the normal force, which is 3.2. So if you do that math problem, the force of friction should give you 0.7 newtons. Okay, so that's an important number. We'll need that later. All right, what about the tensional force? Well, I don't know that one, right? I'm trying to figure that one out. So there's going to be a net acceleration on, net force, I should say, on block 1 in the right direction, okay, in the right direction. But that tensional force, which is going to cause the acceleration to the right, is going to be slowed down, if you will, by this frictional force. So I can set up an equation, F net equals F tension minus the force of friction, and is equal to MA, okay? Let me see if I can simplify this a little further, because I know a few more numbers, right? I know that the force of friction is 0.7 newtons. I know that the mass is 0.325 kilograms, and I don't know A. So really, and this is F sub t minus that, really what this is going to equal is F sub t is equal to 0.325 A. I'm going to start dropping these units a little bit, plus 0.7 newtons. Okay, that is one equation I'm going to be using. Okay, and how did it become plus 0.7? I just added 0.7 to both sides. All right, so that's one equation. Let's take a look at mass 2. What is the force of gravity on mass 2? Well, mass 2 has a mass of 100 grams, which is 0.1 kilograms. So I'm going to take 0.1 times 9.8 for the acceleration due to gravity, and that comes out to be 0.98 newtons. Okay, so that's the acceleration, or I'm sorry, the force of gravity, I apologize. F sub t, we don't know what that is yet, right? We want to figure that out. So I can set up an equation where basically the net force in the y direction is going to be down, right? We know the net force is going to be down, but it's being impeded or slowed down by this tensional force, because basically this block doesn't want to move, right? It doesn't really want to go to the right, so the tensional force is going to actually slow it down. So I could write F net, and let me change colors here so you guys know I'm doing two different things here. Green. F net equals F sub g minus F sub t is equal to MA. Okay, so now let's fill some information in, right? I know the force of gravity is 0.98 newtons minus Ft is equal to the mass of this guy, which is 0.1 A. Okay, I'm again kind of dropping units just to kind of clean things up here a little bit. Now what I can do is, where this says minus F sub t, I can place this equation there, okay, to figure out the acceleration. That's my goal. So I'm going to kind of write this to the left a little bit. 0.98 minus 0.325 A minus 0.7, and I should put units here at newtons, is equal to 0.1 A. Okay. So basically, if I kind of take my newtons and I figure out what that is, that leads me with 0.28 newtons. And then I'm going to bring over this acceleration over here, so I'm going to add 0.325 to both sides, is equal to 0.425 A. All right. So maybe I'll put zeros in front of these just to kind of help people see. So what is A? Well, I'm just going to take 0.28 divided by 0.25, or 0.425, I apologize. So 0.28 divided by 0.425, A equals 0.69 meters per second squared. Okay, that would be my acceleration. All right. Now, that's one part of the problem. Now, what is the tensional force? Well, basically just find an equation to plug A into, and I'm thinking this one's good right here. Okay, if I plug A, or the acceleration, into here, I take 0.325 times 0.69 plus 0.7, I get a tensional force, F sub t, of 0.92 newtons. All right. So these problems are a little bit complex, but if you kind of just take them step by step using free body diagrams, thinking about Newton's second law and determining the net force, they are, I believe, within reach. That takes care of this video. I'll see you guys next time.